Welcome back, everybody. This is part 5 of the Bezier grass series, and today we're going to be talking about wind. So to show off the wind, I've set up a small demo scene here with about 500,000 blades of grass currently being rendered and fully shadowed and everything. So no real optimization happening at this stage, but hopefully you can agree it looks pretty good. So we'll talk a little bit about the features, how this works, and then we will dive into the material graph and kind of break it down piece by piece. So the core design philosophy around this wind system is to control the control points. Rather than most wind, like this existing simple grass wind node in Unreal, when you plug that in, you are directly manipulating the vertex positions, which works fine for creating a sense of motion. But by changing the vertex positions, we don't change the vertex normals. But with our system, we're deriving the normals from the control point positions of our blade of grass, which means that if we were to change the control point positions, we would automatically get our corrected normals with no extra work at all, which is really great. And we can actually see that happening right now if we look at the grass here, kind of in this spot right here in particular. You'll notice as the grass bobs, the specular highlights are shifting. And it will be really obvious when we look at some of these controls. So let's go through the controls. First, I want to talk about the Flutter. So Flutter is kind of the secondary motion, and to look at that, I will turn off the primary motion, or Swell. So with no Swell, we can see we get this undulating look. Here's what Swell kind of looks like as a baseline. It's a variation of a sine wave along the length of the blade. And so we can control the wavelength. I might need to turn this up a little bit. So we can control the wavelength of the flutter. Gives different kind of looks. So I like 0.5. We can control the speed of the flutter. So we can get a slow flutter, or we can get a very fast flutter. That looks terrible. Better. And then the strength. So basically this is wavelength, speed, and amplitude, essentially. So a high amount of flutter will undulate a lot. A low amount of flutter will undulate a little. Find that this works best when it's a pretty modest effect, and you might want to establish some relationship between the amount of swell and the amount of flutter and whatnot, but right now I'm just hard setting everything. And then swell is the large scale movement, and this is probably going to be easier to see if I crank it up a lot, but this is kind of a relatively strong wind, but we can crank it up to be extremely strong, like storm wind. So now we can see that this wind is grabbing our grass a lot and pushing it over in groups. And if we want to view it, we'll turn on this debug here so we can see our Perlin noise panning across the landscape. This is actually 3 different Perlin noises panning at slightly different speeds and directions, giving it a very deep, non-repetitive look. Might be a little bit overkill, but that's okay. And then, so that's the swell. You can really see how the specular highlights are shifting as this grass moves around. Then we have the sine scale. This just globally controls the strength of the effect for both the flutter and the swell. So at 0, it does nothing. 1, we get our full effect. 2, we have doubled the strength. At this point, it's so strong that our grass is mostly getting pushed totally flat. Then we have the strength of the effect at the midpoint and the tip. So if we set the tip strength to 0, we can see that our grass blade is being pinned in place, and we still have the wind blowing the midpoint, which looks pretty goofy, but it does work, right? So we can see that flop around. And then if we set the midpoint to 0, we'll obviously get no motion. We set our tip to 1 and our midpoint to 0. Basically, the midpoint will still move, but it won't move nearly as much because when we look at a Bezier curve, right, if we look at our grass, if we have something set up like this, and our endpoint is moving, our midpoint is still, of the curve is still moving, even if our mid-control point isn't moving. So I kind of like when that is maybe dialed down a little bit compared to the end, but not fully. And hopefully the YouTube bitrate isn't totally annihilating the look of this. Next is the texture scale. So I'll turn on our debug again. So here we can see that texture scale and also randomness. So I'm going to turn off our randomness for a second. So we just get our pure noise. And we can see that at a small texture scale, our noise is very high frequency. And at a large texture scale, very low frequency. And you could potentially put multiple layers here. I'm just have kind of the same frequency across all 3 noises, which probably isn't the most effective use, but that's okay. And then the randomness controls how much individuality the blade of grass has from this noise. So we can see here with our randomness 0, the grass moves exactly in line with our Perlin noise, all uniformly, which can look a little weird and stiff. If we turn up the randomness to 100, now the grass is still moving with the Perlin noise, but it's sampling a slightly different position than its neighbors, and gives it a greater sense of individuality. And if we set it to something very high, it doesn't really look like it's moving in unison at all with wind at this scale, right? Ultimately, the randomness is going to be affected a bit by the scale. You could put a relationship there, like the higher the scale is, the higher the randomness is, to make that a little bit more uniform. But in any case, a high randomness means that our grass looks like it's moving very independently. So I like setting this somewhere with a low amount of randomness that just gives the grass some individuality, but we still get that large sweeping swelling motion. Then we have our speed multiplier, which is pretty straightforward. So there's a couple of things we can do with this. So if I set this to something soft here, we can, let's see, it's a little too much still. So if we set this wind multiplier to like 1.5, now we're getting a very fast wind. But if I very fast wind, but it's not grabbing, with a swell low, it's not really grabbing and moving the grass all that much, right? Whereas if we have fast wind and a high swell, we get this very storm wind pushing the grass kind of ridiculously, maybe too much. But you can tune this obviously to your preference. Whereas if we set the speed something lower, we get kind of gentle rolling but strong wind that's grabbing this grass a lot. If we set it to something very low, that really gentle movement, even if our swell is a pretty high number, our swell is a pretty low number. We just get kind of an ambient look to our grass. And then the X and Y is just controlling the direction of the wind. In reality, you would want that driven by some sort of material parameter collection from a wind blueprint, basically, or however you're controlling the wind globally. You would pass that through into the material to tell it how fast is the wind moving and in what direction. But to keep things simple, I've just simply hard-coded it here. And that covers the controls. So you can see we can get a pretty wide variety of look in our grass. We get nice lighting and accurate specularity. We have this nice layered motion, and we can get both kind of calm and stormy looking grass here. So let's look at the material graph. So it's going to look like quite a lot, but none of it's particularly complicated. And also I did increase the editor scale. I know some of you have had a hard time seeing content with the kind of the resolution of the screen. So I've scaled that up by about 20%. So let me know if this is easier to see for you. So also just a side note, very simple PCG graph that's spawning this grass. We've got 500,000 points that are being spawned and then rotated, positioned, and then the mesh is being spawned. If you use PCG with grass, you'll probably want to turn off ray tracing on that grass, and you'll probably want to turn off collisions. Both of these will be huge wins for your performance, and just not really feasible to do ray tracing on 500,000 blades of grass, nor is it beneficial to have collisions on them, and both of those will slow down the spawn rate of the grass in PCG as well as the real-time performance. So yeah, so let's look at our material. So there's a couple of sections we'll just look at individually here. First is the let's look at the wind UVs and randomization. So the wind UV is being determined by looking at the location of the blade of grass in world space. And rather than using a world position node, we are getting the origin of our blade of grass in instance and particle space, and we're transferring that to world position. Reason for this is we want the same value for the entire blade of grass, right? If a grass is at a specific world position, we want that world position for the whole blade of grass all at once. We don't want the per pixel world position, because that would cause the effect to be applied non-uniformly across the blade of grass, and it can warp the mesh. So we're getting our position. In this case, we just care about the RNG component, and then we are getting our randomization. So in this case, I'm getting per instance random, which is just going to output a value from 0 to 1. I'm using the constant bias scale node to subtract 1 and multiply by 2 to remap that in the -1 to 1 range. And then I'm converting that to an angle vector with sine and cosine, normalizing that, and then multiplying it by our randomness value. So essentially what this is saying is get a random direction and multiply it by a particular value, which will say when we add this to our component pivot location, take where you are in the world and look in a random direction a particular distance from that spot, and that's where we want to sample the texture. Then we're dividing this by our scale factor. In this case, you could multiply if you wanted, but yeah, so here I'm using divide, and this is allowing us to shrink the texture or expand it to get our control there. All of this is being pumped into a panner node, and we have our time obviously going into time, And then our speed controls the, you know, a 2D vector that we're panning in. In this case, I've just hard-coded these and then used parameters, but in reality, again, you would probably want controls in your wind system. I'm using 3 Perlin noises to get rid of repetition. It's probably a bit overkill, but it's the same texture, same RGB texture, and I'm sampling it 3 times. Again, you could just do 1 if you wanted, but by sampling it 3 times and averaging the results while panning them at slightly different speeds and directions, I can get wind that, you know, the swells don't really ever visibly repeat. You could also use like generated noise or whatever, but I just wanted to use texture-based noise for this. Again, think of this as a framework. You don't have to follow everything we're doing here exactly. But yeah, so we're saying here are the UVs that we're generating. Here's our panning direction. Then we pan our UVs, and that's what's giving us that moving texture that the grass blades can sample. Then I'm adding these together and averaging them out using sine to get a, you know, sine wave out of it. And then I'm using constant bias scale just to remap the range. I'm adding 1 and dividing by 2. Then finally, I'm multiplying that by our swell value to get the final swell amount. And that's going 2 places. One, it's going to our debug visualizer down here, which is just blending between red, green, or blue, depending on the amount of swell that we're currently getting, so we can see that Perlin noise. And then the other place it goes is to combine with our Flutter. So the Flutter, once again, looks like this, right? So this is our secondary motion. So we want to combine that with our primary motion. In this case, I'm using a subtraction. There's lots of different ways you could combine these motions. But we are taking the t, so our position along the length of the blade, and we're multiplying that by a factor, and then multiplying that by time, or excuse me, adding that to time as an offset. Then we're multiplying by speed, and this is effectively varying the kind of the speed of the effect along the length of the blade of grass. Then we are adding a randomness variable here, so we're just grabbing our, for instance, random after remapping it, and adding or subtracting that position from this value to give each blade randomness to its flutter. Once again, putting that into a sine wave, and then doing another constant bias scale here to remap that range before altering its final amplitude with this wind flutter value. Those get combined into the subtraction, and then our sine scale is a multiplier that will control the strength of the effect globally. Then we can, again, control the scale at the midpoint and the tip, because both of these are individually being passed into adds to our Bezier position, right? So here is P2, and it's getting added the tip sine value, and P1 is getting our midpoint sine value. So both of these just get pumped straight into our positions, which of course get pumped into our normal calculations and make sure that we are getting normals updated as our grass updates. So that's really all there is to the basic function here. But I did want to talk a little bit about some added functionality. So one thing about Bezier curves is that as you move the control points around, the length of the blade of grass will change. Right, so you can see here, I've got, if I have a straight line from 0 to 0.5, I've got a length of 0.5. This is an approximate length, not like a technically, mathematically perfectly accurate length. But you'll notice that as the grass curvature increases, the length increases, right? So if I bring this up here, the grass has grown by 0.1 to be 0.6 long. And that's not really a desired behavior. It's not particularly noticeable, and this is actually how Ghost of Tsushima shipped. Their grass blades do fluctuate in length as they blow in the wind. But if we can approximate the length, which we can, then we can factor it in to our result. In this case, if the position has moved by this much at the midpoint, then this position needs to be scaled back, right, until we're back at 0.5. And this point here would preserve the perceived length of the grass. So we'll seek to kind of replicate that. And the way that we're going to handle that is with this relationship. Length is approximately equal to 2 times the distance between P and S, which is the origin and the endpoint. This is the chord length of our curve, plus the distance between P and Q, which is P0 and P1, and plus the distance between Q and S, which is P1 and P2. And this is the polygon length. So the distance, the total length of our control points is our polygon distance. If we take 2 times our chord length plus our polygon length and divide all of that by 3, we get an approximate relationship that fairly accurately describes the length of our Bezier curve. It is perfect here at 0, but at different lengths it might be more off. I think the longer these get in relationship to each other compared to the chord length, the less accurate it becomes. So it's not perfect, but it does a pretty good job of approximating the length of our curve here. So we can see, for example, that from here we're traveling from 0 to 0.1 and then back from 0.1 to 0.2, and it's accurately putting that at approximately 0.4. And we have seen that we've traveled about that distance in this curve, despite the fact that our chord length is only half that, and our polygon length is substantially more than that. So it's roughly accurately determining that. So the way that I'm handling that is by, once again, using that same formula. So the distance between P0 and P2 times 2, plus the distance between P1 and P2 and P0 and P1 added together, and then divided by 3. Then I'm taking the reciprocal of that, and I'm multiplying our Bezier curve by it, because before it's mapped into 3D space. And what this is effectively doing is scaling down the size of our curve based off of the length of the blade of grass. So we're saying, if the blade of grass is really long, then we want to scale it back. And if it's short, then we'll scale it up. And this here, this transformation is finding out what the length of the grass should be. So by determining the position of this vector in instance in particle space, if we then transform that to world space, we can effectively read the scale of the blade of grass in PCG, because if that position has changed in value, so if the blade of grass is half the size, then when this transformation takes place, our x will be 0.5, and we can measure that length and multiply by that. And so what this will do is it'll tell us how long the grass should be. Without this would just cancel out the length being created by PCG, and all the grass would be that uniform in length, which is not what we want. So we want to say how long should our grass be, and then we will multiply it by that. So basically, we're kind of resetting the grass to one kind of unit in size, regardless of, what we're, based off of the approximate length. We're saying the approximate length should be 1 unit in size, and then we are scaling it back to its intended size before multiplying it by our Bezier curve, and then doing all the stuff that we did previously. And the effect of that, will be visible here if I maybe go ahead and turn off the Flutter. And then I'm going to turn off the tip. I want you to carefully watch the blade of grass if I increase the midpoint scale. So hopefully you can see that as the grass bends more and more, that tip is retracting back towards the origin. And when the grass blade goes perfectly straight, it extends out. And so this is giving us a pretty accurate and believable appearance of a consistent length. So this is actually a problem that Ghost of Tsushima opted not to solve, but I figured that we could implement it here as an optional feature, and I'm pretty happy with the results of that. So the same is true with the tip activated here. That will move even more, and that shrinks the blade of grass. And so that solves the problem here, where we can see if the same thing was happening. If we look at that approximate length, we can see that as this moves around, or as this moves around, by multiplying our entire graph by this value, we can grow or shrink it to correct for that. So that really should sum it up here. That's essentially all I have for today with the wind system. Again, there's a lot of pieces to it to cover in one video, but as you can see, they're all pretty simple at their core. There's nothing particularly complicated going on here, except for maybe the length adjustment. But yeah, that's that. And we'll continue this series. Next video, I want to talk about creating some per instance randomization to the individual blades of grass, and maybe start looking at larger fields and optimizations. As it stands right now, of course, every single one of these blades of grass is exactly the same, even if they're moving slightly differently. So they're very uniform. So we'll want to break that up. I've also just kind of cheated and positioned them all to be roughly aligned with the direction of the wind vector here. You could, of course, rotate them in the shader to start facing the wind by a certain amount. Give them a certain amount of allowed rotation and have that be dynamic. But just to kind of make this simple, I've just statically put them in a position. If you have them totally randomly rotated, it doesn't look very good because you don't get that kind of sweeping effect nearly as much. So maybe we'll look at that later too. But yeah, that's it for now. Thanks for watching, and see you next time.